All right, so my name is Liu. I'm one of the 3 instructors. So I'm going to teach about the transconductance amplifier and also the next 2 lectures. I think there's one on current mode circuits, I believe, and just one more. Right, first order filters and so on. Okay, so the outline of the lecture today is that we're going to talk about the differential pair. Unfortunately, I didn't set up the sharing properly. So some of the people on Zoom are not going to get it, but I'll fix it afterwards if you can get hold of it. Okay, so I'll talk about the differential pair, the transconductance amplifier, GM, and also the gain A, and how we can also use the circuit as a voltage amplifier. And then finally, because of certain limitations on the circuit, we also show you a different circuit called the wide range transconductance amplifier. Okay, any questions? Okay, so let's look at a simple circuit here. So there are only 3 transistors, right? We have 3 NFETs. You can also make them PFETs. If you do PFETs, then you flip everything around, right? So you turn it upside down and your ground will become VDD, right? So circuit's exactly the same. And of course, there's a difference in how you apply the voltage value to the inputs, and inputs here are going to be V1, V2, right? You're going to compare V1 and V2. And there's a bias current that flows through this circuit, and that's VB. That's set by VB, okay? So which means that now if I want to have a certain bias current, I'm on this curve, right? If I'm sub-threshold. And what am I assuming also? Right, so you can always create a bias current because you know here the current is saturated, right? So I set some particular current that I'm looking for by setting the gate voltage to some value. So say 0.6. And maybe that gives me about, say, I don't know, 100 nanoamps or something. Okay. But if I want to operate this as like a constant current sink, right, then what do I have to guarantee about VD? Can VD be anywhere? Yeah, that's correct. So you always have to guarantee that this drain voltage here is above 4 UT, right? So that means when you look at the circuit there's nothing that guarantees that V, which is your VD, right, is going to be greater than 4 UT. So you always have to set the values of V1 and V2 so that you're sure that V is above 4 UT. All right, so normally when you do analysis of a circuit like this, you assume everything is in saturation. This is the simplest thing, right? You can drop all the 1 minus E, all that stuff that follows afterwards. And so that's a good starting point. Okay, so how do this, so first, yeah, you set the drain voltages so that the transistors are in saturation. Now, the way the differential pair works is that now you have this constant current sink here, and this current is going to split into the 2 transistors, right? Point the 2 transistors. And of course, you know, because the current is going this way, electrons are actually going that way. And so these electrons from the bias transistor are going to flow into those 2 legs. And now, if you look at this circuit properly, you'll see that it's actually composed of 2 source followers. And you learned about the source follower last week. Yeah. So there's one on that side, and there's one on the other side. Okay. Just pretend that the drains are tied to VDD, and then you should see your source follower. Okay, remember source follower, you have 2 NFETs. And again, for the source follower, there's a bias transistor at the bottom, right? So, oh boy, okay. I have to do that later. Okay, so now we can try and solve what I1 is as a function of IB and V1 and V2, right? And so to do this, you use Kirchhoff's current law. You know that the currents flowing into the VS node should be the same as the current flowing out, which is the IB. And assume everything is saturated, or everything's operating in saturation region. So you have I1 equals to I naught E capital V1 minus Vs over UT. Wait, does anybody see a ruler? Okay. Nice. Okay. Easy. And then you've got one more equation. That's IB, right? And IB is I naught E capital VB over UT. That is VB minus Vs, but then Vs is ground, so you can drop it out. And so again, using Kirchhoff's current law, IB should be the sum of I1 plus I2, right? And so what you can do then is you can substitute these terms into here. Yeah, so you can factor out E minus Vs, and then you end up in the brackets E capital V1 over UT plus E capital V2 over UT. So it's quite straightforward. And then you can solve for Vs, which is what you want, right? So you can, actually you want to equate this term to this term, drop the I naughts, right? And then you have EVS, E minus Vs over UT, you put it to the other side. So there's EVS over UT, and then it's E capital V1 plus E capital V2 over E capital VB. Okay, no problem here. Everyone can see this, it's quite easy to solve. And now you need to see how I1 and I2 changes as a function of V1 and V2. So you go and you substitute I1, remember this equation here. So I1 equals to I naught E capital V1 minus Vs. You take this here and you put it into here. Okay. Everybody got that? So that gives you IB E capital V1 over E capital V1 plus E capital V2, and that you divide the numerator by E capital V1 over UT and also the denominator by the same term, and then you get IB over 1 plus E capital V2 minus V1 over UT. So we can see if this equation is correct, because if V2 is greater than V1, this term is going to be positive, right? Which means the current should be dropping as V2 becomes bigger than V1. So is this what we expect from the circuit? So if V2 is greater than V1, then I1 should drop and I2 should go up. Does that make sense? Yeah, it should, right? Because the gate voltage here is increasing. Well, the gate voltage here is higher than this one. You have the same source voltage. So you expect the current to be bigger. Okay, so it's correct. And then I2 is the same, but it's opposite in the sense that it's still IB over 1 plus E kappa, but then you know it's V1 minus V2. Right, and again, you can do a sanity check. If V1 is greater than V2, right, you expect that I2 should decrease. And that's what you get. Okay, so it's good. Okay, and so these are called Fermi functions, the form of this equation. Also, sometimes you can define this as a sigmoid. Now, the other thing is that you can take the difference of the two currents, like I1 minus I2, and then, just put in the equations. This one here minus equivalent of this one for I2. So then you get IB E capital V1 minus capital V2 over E capital V1 plus E capital V2, and that's a tangent function, right? And so what you get is, if you take the difference of I1 and I2, you get IB tangent capital V1 minus V2 over 2UT. Okay. So it's kind of nice. So now you get your tangent, your sigmoid. And those are functions that you see a lot in neural networks. I go one further now. Okay, so then let's plot it. So we can plot how I1 and I2 changes as a function of V1 minus V2, right? So if I'm sitting here where V1 is equals to V2, then you assume I1 should be equal to I2. right? And so you do see that they're at this is the crossing point, right? And if V1 is greater than V2, then as we just looked before, from the equations, we see that I1 should increase as V1 increases, and that's what you see. It increases, and then it's going to saturate IB, right? So depending on where you want the saturation level to be, you can set that by turning VB, right? So that you can set your bias current. And as L1 increases, I2 should drop, because they both sum up to IB. Right, so you get a curve that looks like this, and then you get I2, which is the opposite. And again, remember that the sigmoid is 101 plus B minus something. So you get the sigmoid function using this simple circuit. Okay. Okay, now let's look at, again, I1 minus I2, which we said is IB times tanh of E kappa V1 minus V2 over 2 UT. I'm going to plot this here. So let's call this also I out. Okay, on the y-axis, and here it's a V1 minus V2, right? Again, for a tanh function, if V1 minus V2 is 0, the current should be 0, right? It's a symmetrical function. So that means here you have it at 0, and then if you go on the positive side, then you get this increasing. Again, it saturates at IB, and then if you go to the negative side, then you get it decreasing to minus IB. Okay, so that's the differential pair. Questions?
How do you make sure that yes is the saturational?
Yeah, so you cannot. Actually, the conditions where yes will be saturated, and there's also situations where it won't be, and then you see the shape of the curves change. And so it's something that you'll have to take into account when you set the V1 and V2.
But there's no simple relationship between VS, V1, and V2.
There is. We're going to derive that.
Okay.
Yeah, there is. Okay, so for transconductors amplifier, it's just a differential pair, the 3 transistors here, except now since we want I1 minus I2, the easiest thing is to put a current mirror at the top, right? So you have I1 mirrored to the PFET on the left, and then you get it coming out here on the right, right? And then what comes out here is I out, and I out is I1 minus I2. Okay, so it's quite straightforward. Again, you can make the symbol for the transconductance amplifier. And so there's always a plus and a minus node, right? And also the bias voltage and then the output voltage. Right, again, the V, so how do you know which one is the plus and which one is the minus? Yeah, V1, V2, V out.
So if you have a current mirror, I1 must always be equal to I2. So
Yes.
how can you come up with this differential I out?
Oh, that's because you can move the other way. Yeah, steady state, right? I1 has to be plus I2. But if you hook it to something else that can draw current or push current in, then I1 is not necessarily I2 anymore. In steady state, with nothing hooked up to it, then you're right. I1 is equal to I2. Yeah. So basically, he's asking the question, why do you get I out? And this depends on where you hook this node to, the circuit that follows afterwards. Yeah. If you tie this to a gate of a transistor, there's no current flowing to the gate, right? Then I1 has to be I2. Okay, so how do you know? So if I have a plus and minus, how do I know that V1 is on the plus node and not V2? Because the plus here actually means that if this voltage is increasing, then your output voltage should be increasing. Right, so which is the input voltage that if you increase it, the output voltage will increase? Is that simple or you guys? You want to try?
V1,
V1 what?
I1. The current increases when V1 increases.
Yeah. Then it gets mirrored to this side, right? And then now you have I1 that now there's going to be more I1 that charges up the out. Right, so the out moves on. Okay. You cannot do V2 because if you increase V2, then V out gets pulled down. Right? Yeah.
I don't really understand that. Like, we just get at the output, I
Mhm.
out, okay? But this is connected to nothing.
Yeah, this is
So we
connected
don't-
to some other circuit. Yeah.
Yeah, no, but like now the case.
Yeah, yeah.
And like, we don't know how much like the voltage is from I out.
Yeah, so it's really more, do you get current that's going to charge up that node
Uh-huh.
or it's going to discharge that node? Right, so if you increase V1, then this current will, so let's assume they're both at the same place, right? V1 equals to V2. So then I1 equals to I2. So now if I move V1 up, then I1 will increase,
Yeah.
right? Gets mirrored over here, so it's going to start charging V out, right? Because I1,
Start going-
yeah, so
going,
then it goes out, right? And V out also increases because you're charging that node.
like
right.
I say, if you put a resistor, the out of the resistor.
Yeah,
I-
right. Yeah, exactly.
Okay.
Yeah.
Okay.
Yeah, yeah. And then, so the same thing, so now, so that's why the V1 is on the plus node and the V2 is on the minus node. You have to kind of reason through it because I can ask you to hook up something because, you know, I can do a feedback loop where I tie the output back to something here, to the minus or the plus, and then you have to decide which one it is. Yeah,
If we wouldn't know V out and V1 and V2 would be the same, then I1 and I2 would be the same and I out would be 0.
yes, that's
Okay.
correct.
And then it doesn't matter what we plug in for V out. Let's say we get.
No, yeah, VR will go to someplace, yeah. That's it, that's, actually, VR should go to a place where there's two transistors stay in saturation. Yeah,
So it
right.
has to be somewhere.
It has to be somewhere, yeah, but it doesn't have to be at a fixed voltage, but it has to be somewhere.
What happens if you fix?
You mean if I come in and I actually like put a voltage source on it?
Yeah.
Yeah, well, if it doesn't draw any current,
Yeah.
it probably will. Yeah, then I out is 0.
And if it draws current,
Yeah, then something will change in the circuit so that you balance out all the currents because KCL always applies. Right.
Yeah.
So if there's more current going out, then somebody has to give that current.
so one other voltage has to.
Yeah, exactly. Yeah. That's good. Also remember the thing that you're making an assumption is that IB is always staying at the same value. Like I say IB, but IB is actually could change also. Right, because again, it depends on where VS sits at. Right, if VS sits at a place where this transistor is no longer in saturation, the IB is not the same IB. Okay, so you have to remember that also. But right now we assume everything is nice, ideal, everything is in saturation. Okay, so then in subthreshold, if you look at small differential voltages, less than 200 millivolts, then if you look at a Tench function, you can linearize it to IB kappa V1 minus V2 over 2 UT, and that's now called the GM term. Right, it's a bit like small signal. So then your I out is GM times V1 minus V2. Because remember, GM is the transconductance, right? So it's when you change the voltage, how much does the current change? Right, it's a voltage to current equation. And so which means now your GM is kappa IB over 2 UT. So if you want a higher GM, then you increase the bias current. That's all you can do. But of course, the temperature will also affect UT and so on, but normally you can't change those values. Okay. All right. Now, why would you want to have like a higher transconductance or lower transconductance? Because normally you want to have a higher transconductance, right? Because it means that for the same change in voltage, the same delta V, right? I can have more current, right? And the only way you're going to get this increase in current is by changing IB, by increasing IB actually, right? But if you increase IB, then you also have to balance the fact that you're going to consume more energy, right? So we're always trading this stuff off, right? Because we know that if you increase IB, the output current will be larger, and so things will be faster, but you're going to burn more energy. So if you don't want to burn a lot of energy, then you probably have to drop IB, and then things will charge up slower. There's no free lunch here. Okay, there's also something called output conductance. And the output conductance GD is the change in the output voltage, output current as a function of a change in the output voltage. Okay, again, if you take the subthreshold equation, you can solve what GD is, and you get IB over the early voltage. Did you guys do this already? Yeah, okay. Okay, the same thing is you can do the same thing in strong inversion. And so in above threshold, the output current of the div pair, now I1 minus I2, it's beta over 2 times V1 minus V2. And then the square root of 4IB over beta minus V1 minus V2 squared. Right, this is something I think you have to derive actually later in your pre-lab, I believe. Okay, and then again, you can then look at what the GM is, right? And your GM now is square root of beta times IB. Right, so the GM in subthreshold is just, it's proportional to IB. If you go above threshold, it's proportional to the square root of IB. Okay, so in some sense, in subthreshold, if you increase the current, then your transconductance changes linearly with the bias current, but in above threshold, it's actually the square root of the current. So it changes slower with the change in the current. Any questions so far? All right. Okay. Now this is now the tricky part, right? Where we're going to assume that we take away the assumption that the transistors are in saturation, and then we see what happens. Okay. Okay, to get the Tench function, we assume that all the 5 transistors are in saturation. So we write I1 equals to I0 E capital V1 minus Vs, I2 E capital V2 minus Vs, IB is just capital VB, and I out equals to 1 minus I2, right? So that's a summary of what you learned before. Okay. And it's not moving forward. Okay, is that the one? Yeah, okay. All right. So now we have to look at where Vs is, right? Because Vs will tell you if this transistor is in saturation or not. Okay. So what we're going to do now is we're going to assume that the bias transistor is actually not in saturation. Yeah. And so now you have to write the whole equation for that one transistor, right? So it's no longer I0 E capital VB over UT, but now you have to add now this other term, 1 minus E minus Vs over UT, right? But we'll still make an assumption that these 2 transistors are in saturation, right? Because even though this is not in saturation, this guy's could be in saturation, right? Because their VDS is from here to here, right? And this transistor's VDS is from here to here. Okay, so now you take this term for IB, you put it in here. And remember, it's equals to I1 plus I2. So then you have again E capital V1 minus Vs plus E capital V2 minus Vs. And now you have to solve for E minus Vs again. And now when you solve it, you see that it's much more complicated than the equation before, right? So now E minus Vs over Ut is E capital Ve over E capital Ve plus E capital V1 plus E capital V2. Yeah, it's a bit more messy, I guess. So I'm actually going to put this equation over here because you'll find that it's probably easier to fit back and forth on the slides. Sorry to the Zoom guys, you can't see it. All I'm doing is I'm writing out this equation on the side so that we can refer to it later. Okay. So for the bias transistor to be in saturation, we have to assume that Vs is greater than 4 UT, which means that E minus Vs over UT has to be a lot less than 1. Right? Because this now is E minus to the power, E to the power of minus 4 or greater than that, and that's much less than 1. So which means now this equation that you have, right, which we derived here, the same one, we can set it to be a lot less than 1, right? And then now this is a bit of mathy stuff. So we're going to take just this part only. Yeah. And so that means that E capital VB over UT is a lot less than this denominator term, E capital VB plus E capital V1 plus E capital V2. Okay. And now what you need to do with this equation is you're going to divide both sides by E capital VB over UT. So this becomes 1, right? And then what you get over here is 1 plus E capital V1 plus E capital V2 over E capital VB. Okay, so far it's getting a bit messy. Okay, but you know that this two terms over here is going to dominate the 1. So you're going to now simplify it and you end up with E capital V1 plus E capital V2 over E capital VB is much greater than 1. Did you guys see that, that part? It's okay? Yeah.
So basically, we just put ourselves like not in saturation, we write the conditions to be in saturation.
Yeah, a bit like that. Yeah. And then you have to like make these assumptions, and then you look at which terms are bigger than which ones, and then you drop the ones that are smaller because they're not going to make an impact, right? Because that's the only way to come to a simple equations that you can think about. So in case you guys didn't get that, so you get 1. Just for this one over here, right? If you divide by E capital VB, then it's 1 plus. In case you don't see it. Okay. You're going to get this, and then you know that this term is going to dominate this term, right? So basically I can cross this out, right? And then I'm going to get that simpler equation, right? So this is equation 1. Now let's write equation 2. Okay. All right. So remember, we are interested in Vs, right? Right now, there's no Vs over here. So we have to go back to the things moving up. You have to go back to this equation over here. E minus Vs equals to E capital VB over the whole thing. And now what you do is you can take the log on both sides. right? So if I take the log over here, I get minus Vs over Ut. I take the log over here, it's capital Vv over Ut minus log of this whole bunch of terms, right? And so now I take out the Ut, and so I end up with Ut over here. Do you guys get the? V minus Vs over Ut is, I just board moving away from it. V over G. Unfortunately, you have to keep the Ut, otherwise you'll forget to bring it out. It's kind of, it's kind of a pain to have it all the time. Okay, and now I'm gonna do the log on both sides. Yeah. Like this. Okay, if I do this, then I get minus Vs over Ut is equals to capital Vv over Ut minus the log of V, all that stuff in here. Okay. Not gonna write. Okay, then you flip, sides, right? So, and then you take out the Ut here, right? And multiply both sides by Ut. Well, let's do that first. Then Ut is going to be sitting here, right? And then now I flip the sign because I want Vs. So this is the plus, this is a minus, and this is a plus. That's good. Okay. All right, so then remember equation 2. Equation 2 says that this last two terms here, E capital V1 plus E capital V2 is much bigger than E capital VB over V2. Yeah. And so now we can simplify the terms even more. That's where we're getting to. Okay. Oh, okay, didn't show that last step. Yeah. Okay, so let's do that. So that means it's I'm gonna drop the other term now. So that means it's E capital. Yeah, so now we're here. Okay, now you have to make yet one more assumption. So you're assuming that V1 minus V2 is greater than 4 UT, which means one of these two terms will dominate, right? Okay. So that means that Vs is going to be minus capital VB. Yeah, how I do this? Okay. This is the actual equation. Now you make an assumption. So if you make an assumption that V1 minus V2 is greater than 4 UT, then this will be yeah, and so the log of an exponential is the exponent, and so that gives you plus kappa V1 over UT. Yeah, and then you're gonna cross this out, right? And so that gives you minus kappa VB. Did I miss? Okay, plus, okay. Now, if V2 is greater than V1 by 4 UT, then you flip it around. So now this will actually be capital V2, right? So it depends on which one's bigger. And so then now you can come to this much simpler equation, which is right here. So it looks the same. So it's kappa maximum. So whichever one is bigger, V1 or V2, and then minus kappa VP. Yeah. You guys got that? I hope the people in Zoom can see it.
So this way you assume that Actually, one transistor conducts all the current as ID1.
Yeah. Just to simplify the
But
equations,
you can
otherwise it's too
never,
hard.
literally can never understand what will happen if the gate voltage of two transistor pairs is equal or close to each other, right?
Yeah, again, if you make assumptions about, the saturation, then you can solve for that. Right, but if the transistor is not, if the bias transistor is not in saturation, then the equations will get a bit ugly. Yeah, we usually like to have the simpler equations because then you can reason to the circuit faster. Yeah, right now what this says is that common source voltage is going to be the higher voltage, input voltage minus VB. So wherever you set VB, right, then that would, how do I put it? In some sense, it makes sense, right? If you look at the circuit.
So in this way, only one transistor of the transistor pair will actually be in the saturation region, and the other will be in the linear mode.
Could be in the linear mode,
So
yeah.
you just consider one set, you get a simple
Yeah, exactly. Yes.
ordinary
Yeah,
common source.
right. It's just that current mostly has to go through there, and so that's the side I'm going to consider. Right, because the other side we have little current anyway, so it doesn't matter. But you see later on that if you have to ensure that things are in steady state, then you have to do something, right? Because if I1 has B equals to I2, then something has to happen so that you're the same. So this is BS, and this is BP. Right, so it sort of makes sense because what it's saying is that VS is going to be, if this is the higher one, VS is going to be V1 minus VB. Right. So it makes sense that if also because if all the currents kind of flowing like this, you're back to your source follower circuit, right? And the source follower circuit says that, this VGS here, which determines your current, has to be approximately equals to this VGS. If you have the same size transistors, no body effect, all that stuff, right? So which means that if I'm just talking about VGS, V1 minus VS is equals to VB, right? Ideal case, which means that if I solve for VS, VS would be V1 minus VB. Yeah, and that's what you have at the top. Right. Because remember, so this is quite important, right? If the current here is set by a certain VGS, the transistor that's now taking this current has to have a similar VGS, right? Otherwise, you'll never have the same current flowing through here. Yeah.
That's the case when V2, like M2 is not actually.
The M2, which one's M2 again?
The V2 one.
Oh, V2, yeah. So this is assuming that this guy is not really getting any of the current. Yeah,
Okay.
right, exactly.
And, like,
yeah, it's always like you go to the extreme conditions, you see what happens, and then you ensure that, if I want to solve for this, I just make sure that I have enough room, right?
my other question is like on the map just before.
Uh-huh.
You said that by knowing that which one? That V1 minus V2 was
Greater than 4 UT.
yeah, exactly. That means that we can assume that V1 is much higher than V2, or V2 is much higher than
Yeah,
V1.
right.
Okay.
Yeah, basically you keep on crossing out terms as
Yeah.
much as you can.
And why for UT?
Why 4 UT? Because e to the power of 4, you usually take like a 4 UT because e to the power of 4 is much bigger than e to the power of 1. Right? Yeah. So you see 4 UT keeps on showing up. It's just let's if you do the just solve for it, right? Like actually going to calculate it in the computer, you see that it's going to dominate. So you must well just drop it out. Yeah. And then the 4 UT over here, the VS over 4 UT is because of the subthreshold linear saturation, right? Yeah, definition. Okay, and so now if VS is that, then you know that if you want VS to be such that this thing is in saturation, then you have to make sure that now this is telling you something. This is telling you where you should set the values of V1 and V2 because you're the one in control here. right? It's saying that if you want this transistor to be in saturation, you better make sure your V1 minus V2 is greater than VB. So that means it's saying that if I have, say, 0.7 volts here, right? Then I have to add 4 UT over kappa. Well, let's forget kappa for a moment. So like 100 millivolts. So I have to make sure that this guy is at least, V1 is at least 0.7 plus 100 millivolts, 0.1. At least, the more the better. Right? That means you shouldn't set this guy at 0.6. Not a good thing to do, right? You should set it at least 0.7. Does that make sense? Because as soon, so this is like a common mode level that you have to set. You have to make sure that the voltage is, the common mode voltage is high enough so that this guy can go into saturation.
It's not only for basically we do the sigma curves, right? To cross the curves. The linear region between is probably the one we're most interested in, right?
Yeah.
But isn't this exactly only the the proof for exactly not the linear the region we're interested in? Because they're like the difference between V1 and V2 is exactly below like 200 millivolts or so, right?
Yeah, but no, but that's wait. But we're talking about the difference between these two. Here I'm talking about the level of this voltage.
But we
Yeah.
derive this equation with the assumption that the difference is really small between V1 and V2.
No, we didn't.
Isn't this the one we did on the last slide?
No, this one we're assuming that one of them is much bigger than the other,
Yeah, yeah.
right?
So we came to this equation with that, right?
Yeah. This one says that you, yeah, right.
So, but this is exactly for the regions which we are not interested in, right? Because mostly, I believe, I don't know for what this is used, but I believe, I think the sigmoid in the middle is interesting, right? The linear region.
Yeah.
But this is
Yeah.
only true for the outside region, for this assumption we made.
It's true that if you okay, it's true that for the sigmoid function itself, that for that, sorry, it's the I1 minus I2, sorry, it's the other one. Yeah, you're right. That is this region over here where it switches, right, between one to the other. You're right. Yeah, and what we're talking about is the one that goes outside of it. Yeah, that is correct. But this actually has some. So actually, this is something more than that. This is so when we derive the equations, right? They show you how I out changes is made, right? That's right. How I out changes is function of V1 minus V2, right? We're actually making an assumption that this transistor is in saturation, right? So what this condition is saying is that you have to guarantee that this is in saturation, so you get those nice curves, right? Is that you have to guarantee that this voltage level has to be greater than the bias voltage plus some 4 UT or kappa, right? So it's nothing to do with this transition region. It's saying that to get to those equations, you have to guarantee first that this transistor is in saturation. Because we made an assumption that it was in saturation, but how do you know it's in saturation all the time? Right, and this is the condition for that.
I just feel like we proved the condition for the outside region, because this condition, the way we derived it, that is maybe it's also true for the middle region, right? Would be possible for sure, but the way we derived it, we said that the difference between V1 and V2 has to be small, has to be big. So that one dominates.
Yeah, one
right?
dominates, so you can
One
simplify the
dominates.
equations. Right, you're right,
So
that you
if one
simplify the
dominates, we are
equations.
not proving the basically the
Right.
condition for what we actually need, right?
Right,
What
so
happens
it's,
if one doesn't dominate? Right?
oh, what happens if V1 is not dominating V2? Then you have this,
And then
and
this,
then you have to carry this along, and then it's not the maximum of V1 minus V2, it's gonna be log of blah, 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 right?
and this is where we hit it, right?
Yeah, so it's gonna be softer. I mean, you're right in the sense that it's not gonna be as harsh as this one here, but you don't want to deal with all that,
Yeah.
right? I mean, nobody wants to go compute V1 plus V2, blah, blah, blah. This is much nicer,
Yeah,
right?
I agree.
Yeah. So, so anyway, it's saying that, you know, when you Because what happens is, and this happens quite a bit, is you take the circuit, you assume that it's going to work a certain way because you've learned how to do this, right? Derive equations and so on. And then when you start putting like a more complex circuit together, people forget, right? And what happens a lot is that they'll have a, I don't want to erase my nice equations. Is that I take this here, I take the simple one here. I might drive this, say, through another, this to another guy here, say. And you wouldn't do this because that's a very bad circuit. Right, I've got some reference level, I've got some voltage that I want to compare it, say it's a membrane voltage of some type. Right now you have a V out, and that V out can switch anywhere, right? And so now you don't remember anymore that for this amplifier, for you to use the equations that you've learned for this amplifier, you made an assumption, right? That this transistor, the bias transistor, is in saturation. So you cannot swing its voltage all the way from ground to V. Right? As soon as you do this, the equation breaks down, right? If you're close to ground. And so that's why it's good to remember all these things in your head also, right? So that when you're creating a more complicated circuit, that you also remember that this input voltage cannot swing anywhere that you want to. It depends on the bias voltage that you set, right, for this amplifier. And you probably set the bias voltage for this amplifier depending on how you hook up the circuit. Right. So then you see everything is sort of dependent on each other. Oh,
Can we just like use terminal or something like this just to not depend on the other blocks? Like we just like we did that in another class. Like just
yeah,
do the amplifier of one,
yeah.
and then like derive the expression when you connect.
Yeah, and then you know that, okay, the voltage here has to be from say 0.7, no, okay, say 0.8 to VDD if you like, and then, you know, you don't worry about that. But you have to ensure that it never drops below 0.8 volts. Yeah. So whatever's driving it cannot drop below that level, or if it does, you have to assume that the operation of the circuit will change. Right? But if you assume everything is as you've learned, then you might get very disappointed later, right? And this is the thing is when people do this more complicated designs, they have to keep on thinking about where the bias voltage is sitting, how do you want to set it, why do you want to set it at that value, right? If you want to run things very fast, set this very high, right? Because they're going to run very fast, right? But then you pay because you're going to burn more energy. And then you also go out of sub-threshold, maybe you want the exponential functions, right? So that means you have to bring this back down again, right? And that also sets what V1, V2 can do. Yeah. It's the art of analog design. Okay.
Even for above threshold,
Above threshold, it's more complicated. Yeah, actually, I think in post-like we're supposed to derive the equations.
okay.
It's not going to be as fun. Sub-threshold is so much nicer. Yeah. Yeah, sorry. That's why everybody wants to go sub-threshold. Like you saw the GM is square root of something, right? Instead of just IB. So it's much nicer. Okay. Okay, now this is, yeah. This is also kind of a little bit tricky. Okay. So now we're on the other side. We're saying, where can V out be such that this transistor is in saturation? Because again, we also said everybody's in saturation, right? So how do we know that this guy's in saturation? Okay, so if you want to keep M5 in saturation, it's quite easy. You have to make sure that the VDS here is less than, it's greater than 4 UT, right? So that's VDD minus V out. If you want to keep M2 here in saturation, then V out minus Vs has to be greater than 4 UT, which means that V out, yeah, this is again, you know, making all these assumptions, right? So V out has to be greater than Vs plus 4 UT, and you know that Vs has to be kappa max of V1 minus V2, kappa max, wait, kappa times max of V1 and V2 minus VB plus 4 UT. Right? Is that because you already know where Vs should be for this guy to stay in saturation, right? That imposes where V out needs to be. Does that make sense? It's like they're all dependent on each other. Because if this Vs has to be some value and above, then this one has to be even 4 UT higher, right? Otherwise, this guy will never be in saturation. So that actually points to a problem with this 5-transistor amplifier circuit, which is that you can never get V out to go to ground. Right? This is known as the V-min problem. Because, you know, when you think of an amplifier, you assume that it can go between, you know, the VB and ground. Right? And in fact, it cannot. So the minimum output voltage that you can get will depend on V1, V2, and VB. And so your final conditions are that this V out has to be less than VB minus 4 UT, and it has to be greater than kappa of the maximum of V1 minus V2. Sorry, V1 and V2 minus VB plus 4 UT. And so this is what happens when you plot I out versus V out. Right, so basically you move V out, right? You come in and then you move V out around. And you measure what I out is, right? And here you set V1 equals to V2, right? And all I do is I take the voltage V out, I move it around, I measure what the output current is. Right, you can see the output current is actually not at 0, right? Actually, it's at some finite value, right? And so if you move it too close to VDD, right here, then you see the output current drops a lot. Yeah, because that upper transistor is no longer in saturation. And you move it too close to the other side. In fact, here this is not even 0. This is dependent on VB and V1 minus V1 and V2, right? Then you can see again the current now increases a lot. Right. So ideally, what you want is something that's like this. But you don't get that. If you push it, you know, too much, if you move V out too much from the place where it should be for the transistors to be in saturation, then your output current is going to change in some way that you might not like. Okay. So anyway, we're going to talk a bit more about this because when you run this circuit as a voltage amplifier and not as a transconductance amplifier, there are still more limitations. Okay, that was see. By the way, what time is it? Do you guys have a break or something? Quarter past already? Yeah, God. Do you guys need a 5-minute break or should I go on? Done. Okay, so we're going on to the next circuit, which is the voltage amplifier. And of course, it looks exactly like what you already have. It's a transconductance amplifier. And again, we had looked at this before and determined what the plus and minus nodes should be tied to. Right? Remember, we reasoned that V1 goes to the plus node, V2 goes to the minus node, and then you can then write the equation for V out. And if you assume that it's just a voltage amplifier, there's going to be a gain, right? A gain term associated with the amplifier. So you can just write it as V out equals to A times V1 minus V2. That's all. Okay, so it's quite straightforward. Of course, now you have to compute what the A is, right? And so the A or the gain is the change in the V out over the differential of the change in the input, two input voltages. Okay, and then again, you can split out the terms. So you can say it's DI out over dV1 minus V2 times dV out over DI out, right? You can cross this out, it's back to this term over here. Okay. And you recognize this one? Yeah, we solved it already. That's just GM, right? And you recognize this one, this is GB, right? So that means the gain is just GM over GB. And you know what GM is, right? GM is kappa ID over UT over 2UT, because this is the transconductance. And then the GD is IB over the early voltage, right? So now if you substitute in, you get that the gain is kappa VE over 2UT. Right, so it's very nice, all the IVs cross out. Okay. And early voltage, this could be, did you guys measure this in your lab? Yeah, and how much was it? 40 volts, like 40 volts or so, right? So you can compute what the gain is, right? So say it's 25, just to make everything easy, kappa is 1, right? So 40 volts divided by 25, so it's 50 millivolts, which is 0.05 volts, right? So then you can see it's, what is it? 4,000 divided by 5, so you get a gain of 300.
So this is a loaded amplifier gain. If you connect some low impedance.
Yeah, this is just, yeah. This is just an amplifier, what the gain is. If I change V1 minus V2 by some amount, how much is the output change? That's all. Nothing about loading. Okay. I mean, you probably wouldn't want to use this as a voltage amplifier anyway. Okay, so these are some of the facts with this amplifier circuit. The open circuit voltage gain A increases with the early voltage, and therefore with the length of the output transistors, because remember in your lab, if you increase the length of the output transistors, you get a better early voltage. Yeah? And then the typical subthreshold values are between 100 to 1,000. So the computer was about 800, so it fits in the range. Because of the large voltage gain and transistor mismatch effects, the amplifier is usually used in a negative feedback configuration, right? So we normally wouldn't use the circuit, the 5 transistor circuit, straight as a voltage amplifier, also because of mismatch, right? So we make all these assumptions that the IB here, everything was split up nicely, right? So that it's I1 and I2, I'm sorry, it's IB over 2 and IB over 2 over here if the voltages are the same, but they won't be the same when you get your chip back. So this is all due to mismatch, which we'll talk about later also. Okay, and so normally what you do is you use a negative feedback configuration. So can somebody know how you would hook this up in the simplest negative feedback configuration? Here's V1. What's the simplest negative feedback circuit you can make from here? VR type 2? V2, yeah. Here we go. You don't even need V2 anymore, right? And this is a unity gain amplifier. Anyway, unity gain amplifier. I swear this board is trying to run. Okay, that's great. See? Also, this is a follower circuit, we call it that also. And you're gonna learn also in the next lecture that we will use this to make a filter circuit. Okay. Cool. All right, so in open voltage mode, used mainly as a comparator, VR is higher than V1 is greater than V2 and vice versa. All right. Okay, this could get slightly painful. Okay, so again, there's the limits of the voltage swing. Yeah. So if V1 is greater than V2, then the current, so again, you make the assumption if V1 is greater than V2 by 4 UT, then the current to M2 is much smaller than this one. So basically the current mostly flows through here, which means VR will get close to VDD, right? And so then M5 will go out of saturation. And if you make V2 greater than V1, then the current that flows through here would be the one that flows to IB, right? The forward current through M2 here, right, has to be greater than the current through M1. Now this is now a tricky thing, right? Because this current mirror here is going to force the current flowing through here to be the same as the current flowing through here. Right? If you didn't have this mirror, then it was okay. But since you put this mirror, and assuming that now there's no output current going anywhere, right? The current flowing through here has to be equal to the current going through there. Yeah. And so if V2 is much greater than V1, this voltage drop here has to be very small. Right? Because we know there's very little current through here, and that current is getting mirrored all the way here, which means now you have to match that current, right? Which means that the only way you can drop the current flowing through M2 is by making the VDS small. Yeah. Well, the VG, this you're feeding V2, V1, and VB, right? The rest of the voltages in the circuit have to move to a place where everything is okay, right? So basically, because of Kirchhoff's current law, the current flowing through here has to equal to the current flowing through here, right? Here we're assuming there's no I out anymore, right? It's just a voltage amplifier. So which means that this current is going to be small because it's mirroring whatever flows through here, which means that now I2 has to be small also, right? And the only way I2 can get small is if this VDS is small. So it's saying that the V out is going to move very close to VS. Right. So remember this curve. I versus VDS. Right. So if I need to have a small current, so this is some VG here, which is equals to V2, right? This is what we have here. So now we say this is IB, right? Just for a moment. Say this is IB. Okay, then if I cannot have IB flowing through, right? I need, because I1 is very small, then this VDS has to move in, right? So that this transistor now puts out a very small current also, whatever I1 is. Get that? Because it's steady state, there's no other way to go. And so that's why V out will be close to VS. It's not exactly VS, but close to it. And M2 goes out of saturation. Right. So here's a case where you cannot assume that all the transistors are operating in saturation.
So is there any contradictions? Because the first, you think that the solar current through M2 is much greater than M1. And then you say that the two current is equal.
Yeah, so this is the normal case, right? If V2 is greater than V1, then this would be true, right? But because you have the current mirror on the top, this cannot be true anymore. Okay, yeah, that's what I'm saying. Yeah. Okay, this one I did go to this. Okay. So now if you assume that V2 is greater than V1 and V out is approximately VS, then if you take this equation that you have from a few slides ago, right? Remember E minus VS is something here, right? Then you, actually I made a mistake. So then again, you assume, I have to fix the slides. I saw there was a mistake here. Now I see I didn't fix the rest of it. So if you assume that V2 is greater than V1, then this term dominates. And so this is actually E capital V2, sorry. All this is V2 over here. All right, so actually, you're kind of like adding these two terms together, right? So then you get 2 E capital V2 over UT. Then you divide top and bottom by 2, then you get 0.5, 0.5 over here, and this is E capital V2. Yeah, this is very tricky. Okay, so this is the case where V2 is greater than V1 and VR is now close to VS, right? Because the current mirror is forcing. This is only for the voltage amplifier case, not the transconductance amplifier. Because transconductance amplifier, you're actually putting out current or you're actually sinking current, right? Here it's a voltage amplifier, which means there's no IR. So IR is just 0. Right, so that means all the currents have to balance out. So which means this current flowing through here has to be equal to this current.
But if V2 is much greater than V1, you should ignore the V1 term instead of adding.
Yeah, the problem is this equation. See, this equation actually is assuming that this transistor is in saturation, but it doesn't have this, you know, this VDS being very small. Yeah, right. So actually what we said before is not quite true in this case, you know, because this equation that we derived was from the case where when we assumed that everything was in saturation. Yeah, so here we assume that it's going to be about the same because remember we said the currents flowing through here and through here are about the same. I should say on this side, right, they should be about the same. So we have to assume that the currents also are about the same, which means the E cap or whatever is going to be about the same. It's assuming the VDS is not in there, because if the VDS is in there, then it would give you the proper current, right, for this case. Okay, so let me go back one here so you can get it. So remember we have this one here. The top current mirror forces it to be about the same, right? We didn't say anything about what ID is, by the way. We just say it's about the same, which means that since they have the same source, right? So we assume that these two terms are about the same also. They're supposed to be about the same. Even though you are right, if you just take the actual values, V2 is greater than V1, it's not the same, right? But it's taking into effect that we're missing some term over here that accounts for the lower VDS over here. So if you write it up properly, then you probably would get see that there's something similar. Yeah.
Isn't this the formula for the outside the rate? I think this is the.
Yeah, this is the formula. This is the formula for where VS is. If we assume that V2 is greater than V1 and VR is close to VS.
I mean, the top one is the general formula for.
Yeah, this is the general formula, right? That's what I was trying to say.
Yeah.
This is the general formula that does not take into account that this transistor is not in saturation.
Isn't this the one we wrote with it being not in saturation?
I think this is M3 not in saturation.
Oh, yeah, it was written with M3 non in saturation. That's correct. Yeah, it doesn't talk about this one.
Yeah. Okay.
Yeah, this was, yeah.
Also, okay, that's
Yeah,
why. That's
right.
the contradiction.
Yeah, so exactly. So it's a bit kind of, yeah, just assuming this one is saturation and this one is not. So anyway, for the moment, let's assume that they are the same. Okay, I mean, you have a valid point. Let's say they are the same, but it's because we're not having certain terms in there to get the proper. I mean, if you want to go back, you can write out all the proper equations, right? Assuming that this is not in saturation and this is not in saturation, and then you can see what it looks like. It's just kind of ugly to write them. And so anyway, we just made the simplification. It's just off by a factor of 2 anyway. And it's just trying to get to the case of this curves over here, right? Which I like to show next. Maybe I should go to this curves here so that you understand why I'm showing those equations. Right. So what we see here is a set of curves where you set V2 at some value, right? 0.5 all the way to 5. And then for each of these curves, you sweep V1, right? And then you measure V out, right? And what you see is that you don't get either VDD or ground. You get this thing where it stays at ground and then it gradually moves up and then suddenly goes to VDD, right? And it's trying to, and so the equations before is trying to show you that there is a reason why this is happening, right? So if I take, say, V2 equals to 3 volts, right? If I make V1 around 3 volts and just slightly above 3 volts, then VL goes to close to VDD, right? But now if I move V1 further down, you expect it to hit ground, right? This is what you expect from voltage amplifier. You want to switch from ground to VDD. As soon as V1 is less than V2 by some amount, I should go to ground. But it doesn't, right? You see that it actually goes along some linear line, and then at some point it hits ground. If I set V2 to 2.5 volts, then V1 hits around 2.5 volts and less, right? It doesn't drop to ground, but it follows this linear line, then it hits ground. But when it's greater than 2.5 volts, you hit close to VDD. Now, if you set V2 to 5 volts, that's the worst case, right? Then you see that, well, okay, V1 is trying to hit VDD, doesn't, but when V1 is less than 5 volts, you can see it follows a different line, right? Then it hits ground. So it's not like a perfect voltage amplifier in the way you would like it, right? You set a voltage amplifier, what you would like is here's V1, here's V2, right? I set V2 to some value, say 2.5 volts, right? And your assumption is that when V1 is greater than 2.5 volts by some amount, then this V out should go to close to VDD, right? Or 5 volts in this case. And then if V1 is less than V2 by some amount, then you expect this to go closer to ground by 0 volts. But you find that it's not true. Right? When you do the actual measurements, right, you find that it follows this curve and then it hits ground at some point. And all these equations that I show on the slides before are to show that we can derive them, right? Because what you need to do is to make assumptions that certain transistors are under saturation, and then you have to simplify them, and then you'll see this relationship showing up. So you'll take some time to sink in, so don't feel frustrated, because this is something that even when I was learning it, it took about 2 weeks to really appreciate that this simpler ideas that you have, when people draw symbols like this and you make certain assumptions, they don't hold true when you actually look at the circuits, right? And then you try to understand why it doesn't hold true. Why does it not go blam all the way to ground, right? And so then you have to write out the actual equations for the transistors, solve them, and then you see this dependence. Okay. All right. I mean, partially you can kind of see you'll never be able to run it close to ground, right? Because this guy has to stay in saturation, which means you'll never go to ground, because the VR here has to be higher than this guy in the first place. And if I move this guy up, or this guy up, right, then this VS is going to follow, right? If VS goes up, VR cannot drop below it. There's no way for it to drop below it. So you know it's going to, be some value that's in between, depending on where V2 sits. Right? If you just want to, not write the equations, but just reason through it, right? So it all makes sense, right? You can never drop this below this guy. It's just going to follow what VS is doing. And that's what you're seeing. Okay. All right. Yeah.
Is that the new relation?
Yeah.
Is it that actually just yes, like the other?
Yeah, it's because VS is following V1 now. Right. Exactly. So now the VR has to follow VS also. Yeah. Yeah, sometimes it's just nicer to reason through it, see what you can I guess from the reasoning, whether it matters when you measure. And then if you really want to write equations, then you go through and you grind through all these equations and simplify it and so on. But does this make sense to people that you're doing right? Okay, good. You guys are brave. Okay. All right. So there we go. Now we have the transconductance amplifier. So now I'm going to show you, this is the last circuit, right? So we already said that the transconductance, we're going back to the first circuit, the transconductance amplifier. So we say something nice about this circuit is that it's good. Okay, the good parts of it, it's simple and cheap, like 5 transistors, only one bias voltage that you need. The bad is that the output voltage is restricted, as we saw, there's a Vinian problem, right? And also the voltage gain is limited. So basically, how do I have a new circuit where this output can really swing all the way from ground to VDD, or close to ground and close to VDD? Right, so you have to change the circuit. And the way that you change the circuit is this next one. Of course, now you need more transistors. Right. But you take the diff pair again, the 3 transistors, and instead of taking the p-FET current mirror to subtract both these currents, you actually have 2 p-FET current mirrors, one for the left side and one for the right side. And then since you have to subtract the currents, you have to mirror one of them yet one more time. Right, and so this is done by the N side down here. Okay, and so then now you have a voltage here where you can swing closer to ground into VDD. Right, there's no bias volt. You know, the other one you had which was over here, right? Remember, the output cannot drop all the way to ground because that affects the bias transistor and so on. So if you do this, then there's nothing that stops it from going even further down. Okay? And so, of course, you pay because now you have 2 extra mirrors. If this is more important than
This is you reverse the polarity.
yeah, right, exactly. It's true. So the good thing about the circuit is the output voltage is unrestricted. The gain can be greater than 10,000. The bad thing is that it's the largest circuit, more transistors. Now you have to do 10 more. This is not 9 transistors. And also you have more mismatch. So every time you have the current mirror, you have a chance of mismatch, right? And mismatch comes about because of fab reasons, right? Because when you draw 2 transistors that look the same, they're never going to put out the same current once you get the chip back, right? Even if you drive them with the same voltages. And if you have now this, so for mirror, you always make an assumption that the current that flows through one of them, right, the input side, let's say the output current is the same as the input current, right? Because of mismatch, this is not going to be true, right? Because this is not going to be I2, it's going to be I2 plus something, right? And then now you come through here, you're going to mirror it through here, so now it's not even I2 plus the something, is going to be plus something else, right? And so that means that voltage is going to move someplace that you don't expect it to. That's why you always put it back in a negative feedback loop, because it will find the right place to be. So you don't want to run an open loop like this. Okay, and that's the last circuit. Besides the unity gain amplifier, because you're very quick at it. So, yeah.
Could you explain one more time why the health system is stated right now? Like,
Oh, the 500, is this one? Yeah, so if we go back to this one. Right, so the short answer is this V here has to be greater than 4 UT for this thing to run in saturation, right? And this V also has to be, this V will also follow the lower of the input voltage that comes in, right? So that V also is going to move around, right? Now this transistor over here has to have a VDS that's positive, right? So this V out has to be higher than V, right? So since this can never go to ground, and then it also has to be graded by some amount, then this output will never go to ground.
And I'm just connected to the ground.
Yeah, right, yeah. Because otherwise everything will flip around now. Yeah, so for this one, this voltage here, it can go very close to ground. It just needs to be 4 UT, right? And then this guy is always going to be in saturation. It can go all the way to VDD minus 4 UT because this guy will always in saturation. That's all we have to deal with. With this other one here with the 5 transistor, it's not just that. Right, this voltage here, yeah, it could be 4 UT and above, you can guarantee this, but this voltage also moves around, right? Because it depends on what values this input voltages are sitting at. And which means also that now this V out has to be higher than V, right? So you'll never be able to go to ground. It's amazing how 5 transistor circuit can occupy so much thinking. Like this, but the nice thing about a simple circuit, it tells you even with a simple circuit, there's all these regions you can end up in, right? And it's always because some assumption of yours breaks down. Then all the current relationships change, and then you don't get something like you expect to. And then you have to understand why that's happening. And then over time, if you're an analog designer, you kind of know, right, not to do certain things. But you cannot teach that to somebody. You have to do the design, suffer in some way, and then you remember it, sticks in your head. I mean, now what I'm telling you, all these equations, you go, oh God, the assumptions, this and that, and so on. Because usually after you do a design yourself, that you appreciate certain things that you cannot do. Yeah. Or where your voltages should be set and so on. Otherwise, you're going to expect this beautiful curves all the time. No matter where the voltages are. You can actually do it to your lab. You can, now that you've learned a little bit about reasoning, you can purposely do something. Right? You can purposely, for example, set the common mode voltages of V1 and V2 to be a lot lower. Because we derive where they should be, right? Just set it a lot lower and see what happens. Let's see what changes. If anything changes. Okay. I think that's it for me. Any other questions or? Okay, thanks guys. If you want so next week what I'll try to do is to give some example of how a lab write-up should look like, and maybe we'll discuss some of the pre-lab questions from one of the early labs, like the sub-threshold, super-threshold, so that at least you get some sort of feedback. Is that good? We'll spend about 15-20 minutes on that, okay? All right.